In this paper, we introduce a novel updated Lagrangian enhancement for XPBD called XPBI, enhancing position-based dynamics capability for simulating complex inelastic behaviors governed by continuum mechanics-based constitutive laws. Our contributions include an updated Lagrangian augmentation for XPBD that tracks meshless deformation gradients and per-particle constraints. Position-based inelasticity, a fully implicit plasticity-aware algorithm capable of handling continuum mechanics-based elastoplastic and viscoplastic laws. An investigation for practical stability enhancements, such as XSPH and position correction, and validations of our method with various practical examples. In our method, we track the evolution of the deformation gradient in the updated Lagrangian view, transitioning from initial configuration to updated configuration, with current configuration serving as the reference state. This facilitates tracking large deformations accurately. The solid line loop depicts iterations of our XPBI algorithm to simulate from time tn to tn+1, alternating between an XPBD iteration and a fixed point iteration. During iteration k, current trial deformation gradient is first estimated based on the current gradient of velocity field. Then, plasticity is applied through projection to obtain elastic deformation gradient within the yield region, and finally, velocity field is updated by solving constraints. We evaluate our fully implicit plasticity treatment by replacing it with a semi-implicit method. The semi-implicit approach can lead to severe artifacts. In contrast, our method fully incorporates plasticity in the XPBD iterations and avoids such artifacts. We conducted a hydraulic test on a highly stiff aluminum wheel to validate the importance of position correction. Without position correction, areas with significant deformation and stress suffer from gradient estimation errors due to uneven particle distribution, resulting in artificial fractures and eventually simulation instability. In our method, parameters are intuitive with physical meanings. For example, we can easily control the fluidity of viscoplastic goo. A smaller mu gives a more fluid-like appearance, while a larger mu leads to more elastic behavior. Upon impact with a ground plane, the shear thickening material exhibits low flow rates under high stress, behaving elastically and bouncing off. Conversely, the shear thinning material flows immediately due to its higher flow rate, controlled by the H parameter in the Herschel-Bulkley constitutive model. We compare XPBI sand with both vanilla XPBD and explicit NPM. The vanilla XPBD fails to replicate the correct friction angle accurately, and NPM shows sparsity, clumping, and uneven particle distribution. In the two sand blocks collide scenario, our method also avoids the artificial grid delta X gap phenomena typically caused by NPM solvers. We also plotted the average distance between each particle and its nearest neighbor per frame. Our method maintains both the relative distance and variance stably throughout the simulation. We simulate viscoplastic monsters falling to the ground using varying numbers of particles, showing consistent behaviors. The running overhead of our algorithm decreases significantly as the number of particles increases, showing strong superlinear scalability. Now, let's take a look at our demos. Thank you for watching.